Well, hi again, this is Bob, and I'm continuing to cross my fingers that I don't lose my connection again as I did earlier. We're going to finish off section 5.4 at the bottom of page 295 with something called the geometric distribution. If this seems like it's maybe extra straightforward or something logical, it's because we've seen it before. It's sort of fancied up in a formula, but we've dealt with probabilities and multiplying them together before. And I'll start off by, I'm going to go through this as sort of an intuitive presentation, and then I'll use the formula they gave us for this geometric distribution. They tell us that the distribution, this particular distribution, is used when we have an experiment that has two outcomes and is repeated until a successful outcome is obtained. So it's, you know, we've seen this before where we have a probability of success where we normally use a P, and then we have a probability of a failure, which we sometimes it's just a representative variable, can call it like a Q, okay? But the important thing to remember is that 1 minus Q is equal to P. So if you know and of course 1 minus P equals Q, but we know that the probabilities for a given event, especially since this is like a binomial situation, only has two outcomes. And in this case, recall what we want to do. We want to, we're going to have a number of trials, and we want to figure out the probability of a success occurring on a given trial, or what the book is calling the, where'd that darn thing go? Well, they're calling it like the nth trial. And as always, I'm probably using way too much time to explain this, especially if you've read it already. But this is going to have something to do like with a flip of the coin or a roll of the die. That would be the simplest two situations, where let's say we flip a coin and we want to know the probability of getting ahead on the third toss. Or we roll a die and we want to know the probability of getting a 4 on the second toss, okay? So let me just do a couple of sample problems, and then I think the best thing to do would just be come back and show the sample problems with the new formula, okay? But you could probably work these questions with what we know already without using the formula. And quite frankly, I'm not sure I would need the formula to work these questions, but the book feels it's important to introduce this to us. And on the top of 296, they tell us, they give us sort of the ground rules for this geometric experiment. It has to have each trial has to have two outcomes that can be either a success or a failure. We've used P and Q for success and failure. And recall that 1 minus P equals Q, and 1 minus Q equals P, okay? And then they tell us the two outcomes are independent of each other. Think about rolling a die and flipping a coin. The probability of success is the same for each trial, and the experiment would continue until a success is obtained. Okay, so I'm not going to use the formula now, but let's look at the example 534 for rolling a die. And what we're going to do is we're going to pretend we don't know about the formula, and we're going to do this with what we've learned before in a previous section in either chapter 4 or chapter 5. A die is rolled repeatedly. Find the probability of getting the first 2 on the third roll. Okay, and remember that the number that we're interested in, the die has 6 sides, and we want to get the first 2 rolls not to be a 2, and the third roll to be a 2. Okay? So, since a die has 6 sides, and we don't want to, and remember, this is when we're having one event after the other, we multiply the probabilities together. The probability of not getting a 2 on the first roll should make sense to be 5 out of 6. The probability of not getting a 2 on the second roll should also make sense to be 5 out of 6. Now, the probability of getting the 2 on the third roll, which is the way they've defined the problem, would be 1 out of 6. Excuse me. So how would we compute this? Well, it would just be 5, 6 times 5, 6 times 1, 6. And that would be like 216 on the bottom over 25 on top. Okay? And this is all done on the calculator. But notice the way that they set this thing up. We know we got our correct answer without using the formula. Now let's go take a look at the formula, which says the probability of the event occurring in a given, excuse me, this is right toward the top of page 296. P is the probability of success on each trial of a binomial experiment, and N is the number of trials at which the first success occurs. Then the probability of getting that first success on the nth trial is, so notice what they've got here. We've got the probability times 1 minus P, that's actually failure if you recall, and then our exponent becomes N minus 1. Now, this formula looks like there's a lot happening there, especially since we just did this question by what we've learned from a previous section. So let's go do this exact same problem, which we already know that the answer, the intuitive way, was 25 out of 216. And I'll write the formula one more time. Okay, so let's go back and look at the question we just had. The probability of the 2 occurring on the, excuse me, the 2 occurring on the, what roll? The third roll, we just did this, on the third roll, would be equal to the probability of a 2 coming up, which is 1/6. Now, remember, 1 minus 1/6, that's like our Q, or failure, and we're supposed to take that to the N minus 1, and remember we wanted to get it on the third roll, so the 3 minus 1 becomes our exponent, so we have this. And that would look like this when we simplify it. I'm putting some extra steps here. Okay, doesn't this look exactly like what we just did? In fact, I'm going to point it out here. 1/6 times 5/6 times 5/6, which is what 5/6 squared means, is going to give us 25 over 216. Okay? I personally find it easier to just do this thing intuitively, but we've got to go with the book at least when we're explaining it using the formula. So that would be, let's use this, let's do the next question, the what I would guess intuitively, and then we'll do it with the formula, and this is example 535. This will be the last example, by the way, and I think I've given you 1 or 2 questions on the homework. Okay, in the U.S., 42% have type A blood. Okay? Okay, of course that means that 58% don't, but we'll get that in a minute. So here's what we're going to do. 4 people are selected at random. Find the probability that the first person the fourth person is the first one selected with type A blood. So I'm going to do something like this. I'm going to write not A times not A times not A. Here's the first 3 people, and then the fourth one would be A. And this is, remember, this is the intuitive way. And if we have multiple events, we multiply them together, you may recall, to get the probability. So remember that 1 minus 0.42 equals 0.58. And if there's a 42% chance somebody has type A blood, then there's a 58% chance that they don't. And remember also that the fourth person is supposed to be the one that does have type A blood. So this is the intuitive way to do the question. Okay, then we'll put the formula on it. So this would be 0.58, and the next one would be times 0.58, and then the third one would be times 0.58, and then that last one would be 0.42. So another way of saying this would be like 0.58 times itself 3 times 0.42, and that turns out to be 0.082. All right, so that's the intuitive way. Let's go do this question the way that the book wants us to, or is presenting it. And that would be the probability of the fourth one. So the first thing we need to do is get that probability again of type A, which is 0.42. Actually, I take that back. I'll write the whole formula again, just to be as complete as possible. Okay, so we want the probability to be the fourth person, and the probability of type A blood is 0.42. So remember that the complement, or non-type A blood, was 1 minus 0.42, and then this will become 4 minus 1. The next step would be to go, the probability of that fourth person being type A would be 0.42 times 1 minus 0.42, which is 0.58, to the 4 minus 1, or 3. That's exactly what we did with the intuitive way. And again, this comes out to be the same answer, 0.082. Okay. Thank goodness, knock on wood, because I'm not all the way done yet, but thank goodness there were no interruptions or loss of connections. So I will be back shortly with what I'm considering the most interesting and important part of the class, and that will be the introduction to the standard normal distribution tables. So I'll be back shortly. Thank you.